Now, no, it's still 1:15. I'll just complete one more topic of knapsack problem itself, which we all know, and we all have seen the greedy approach of how to solve knapsack. So that the same thing will just take up. It's very easy. It will not take that much time. The only difference is that uh, we call this as 0-1 knapsack. Now, the knapsack of greedy programming approach or greedy strategy was he had uh, some items with some weights and a profits associated with it. So here we have 3 items and its weights are 2, 3 and 4, and profits associated with it is first item is 1, second item is 2, third item is 5, and if you remember, profit is nothing but it can be dollars, rupees or whatever units it has. And there is a maximum capacity for the sack or for the bag, and we can put things into that bag, and it has to be these items has to be placed in such a way that the capacity should not exceed the capacity of the bag, and we should have maximum profit. So this is a maximization problem. So the problem of knapsack is same, but the thing what we saw in greedy approach is that we were able to place some part of the item. Like for example, if item 3 is having 4 kgs and there is no space in the sack for placing 4 kgs, but there is a space for 1 unit, 1 kg, then a part of this, that is 1/4 of item 3, could be placed in the bag. So 0.25 units could be placed in that. So that is why we call that as fractional knapsack. But here in dynamic programming approach, or here in this 0-1 knapsack, 0-1 means either the item is included or the item is not included in the knapsack. 0 means the item is not included. 1 means the whole item is included. Here we cannot divide the items into fractions to fill the knapsack. So there in greedy approach in fractional knapsack, if you see, we could, to attain maximum profit, we could fill the bag equal to the capacity. Fill all the items equal to the capacity. Even fraction was allowed. But here in this case, in knapsack problem, 0-1 knapsack problem, we will not be able to every time achieve or fill the knapsack with its maximum capacity. That is in this case 6 is the maximum capacity. So let us look at how to solve this knapsack, 0-1 knapsack problem using dynamic programming approach. Now actually, knapsack can be solved using greedy. This 0-1 knapsack, that is fractional knapsack, what we call. 0-1 knapsack can be solved using dynamic programming. It can be also solved using backtracking approach, as well as it can be solved using branch and bound approach also. So here we are trying to look at the dynamic programming approach of solving the 0-1 knapsack problem. Now we have the equation just as the equation what we have seen. This is known as iterative equation actually, what we have seen in the Floyd-Warshall's algorithm or all-pair shortest path algorithm. The same way we have this equation over here. Now I'll just explain the meaning of this equation later. Let us try to start with the set S0. In all-pair shortest path, we were taking A, that is the matrix. Here we are taking set S. The initial set S will contain nothing. 0, 0, which is nothing but 0 is the profit comma 0 is the weight. So S of P comma W, a set which will be having tuples of P comma W, or elements P comma W. P is the profit, W is the weight. So initially it will be 0 and 0. Nothing is there in the knapsack, so profit is also 0. Then we will take up the first item, which is nothing but item 1. Its P1 comma W1 is 1 comma 2. 1 is the profit, 2 is the weight. We are writing profit before weight, 1 comma 2. Then we try to create a set S0 of 1. I is 0 right now. We try to create S0 of 1. Now how is S0 of 1 created? Using this. You will understand minus Pi and minus Wi later. So S0 of 1 will be created. S0 means it has to be created using these values of S0 set. By taking the element of this set and adding it with this 1 comma 2 or P1 comma W1. So you have 1 comma 2 has to be added to 0 comma 1. So here we have P comma W, which is S0. From S0 we have 0 comma 0, then has to be added with P1 comma 2. So added in the sense profit will be added separately and weight will be added separately. So adding is nothing but 0 plus 0. That's not the case. Profit of S0 will be added separately with P1. That is, we are putting now element or item 1 in the knapsack, which will give us 1 as the profit and 2 as the weight. So this will be the element of S01. Now there is no other elements here, so we have created this set S0 of 1. Now we will compute S1. S1 means we are adding the second item to the set. So actually adding will be S1 of 1. So S1 will be nothing but concatenation of this S0 and S01. So S1 will be element 0 comma 0 plus element 1 comma 2, plus in the sense union actually for the set. So now S1 will be with 2 elements. Now we need to calculate S1 of 1 same way as we have calculated S01. So S1 of 1 will be adding P2 W2 to S1. So we have 0 comma 0 which is added to that, 2 comma 3 is added. So what we have is 2 comma 3 itself. So 2 comma 3 will become the first element of S1 1. Then we have the next one as 1 comma 2. To 1 comma 2 2 comma 3 will be added. Remember again I told you when we add profit separately. So 1 is the profit, 2 is the profit here, that's 3, and here we will have 3 comma 5. So we add separately, profit separately, weight separately. We're just combining them and saying that that's the result of the set or the element of the set. So now all are computed for when the item 2 has been added to the knapsack. Then what is S2? S2 will be, as S1 was union of S0 and S01, S2 will be union of S1 and S11. So S2 will be these 2 elements from S1, union of these 2 elements from S2. Now 2S2, are there any more elements left? Yes, there is. That is, the third item is left. That has to be added to the knapsack. So when we add third item, its profit is 5 and weight is 4. That has to be added to this S2 to get S S2 1 to get S2 1. Now it's the same procedure. We take first element 0 comma 0. We add 5 comma 4 to that. So what we get is the value 5 comma 4 is there, that is stored here. Then what we do is we have the next element has 1 comma 2. So to 1 comma 2 we add 5 comma 4. So what will be the result? 6 comma 6. So this way we will have 4 elements in the set S2 1. 4 elements in the set S2 1. Now once we compute all this, I have already computed this and I'll just show you the final result here. So this is the final result. What we get when 5 comma 4 is added to S2, we get S2 1 with 4 elements. Now what will be S3? S3 will be all the elements of S2 union all the elements of S21. So this is S3. Now do we have any more items that can be placed? No, there are only 3 items that has to be placed in the knapsack. So we have computed till S3 starting from S0, which is the initial set. Now from this set S3 we have to find the actual maximum profit and what is what is placed in which item is placed actually. So let us look at this set. Now starting from 0 to 0, we will examine each element. Now let us look at the weight part first. So these elements are nothing but profit comma weight. So this is profit 0, weight 0, profit 1, weight 2, profit 2, weight 3, profit 3, weight 5, profit 5, weight 4, profit 6, weight 6. Now weight 6, weight 4, weight 5, we are still within the constraint. The maximum capacity on our knapsack, that is M is 6. But here, profit is 7, weight is 7. Is it possible? No, we cannot. So this cannot happen because weight cannot exceed more than the capacity. So this computation is wrong. This doesn't yield us the result. Then what about the next element? 8 comma 9. Profit is 8 and weight is 9. Is it possible? No, we have 6 as the maximum that can be filled up. So this is also not possible. Okay. Then what is left out? The last element. It is 6 comma 6. 6 is the weight, maximum capacity is also 6, no problem. This is absolutely fine. 6 comma 6. Now let us start from the beginning itself. So one thing is we eliminate those elements from the set which exceeds the profit. Which exceeds the weight, not profit, sorry. We eliminate the elements which exceeds the weight. So 7 comma 7 and 8 comma 9 has been excluded. Now there is another thing which we need to know or apply is known as purging. Purging. It says purging rule. Now what this purging rule is, let us look at the first element and the second. Profit is 0 for the first element, profit is 1. Profit is increasing. Weight 0, weight 2. Weight is also increasing. So there is no problem. Then we compare the next 2 elements. Here also profit is increasing, weight is also increasing. No problem. Then next 2 elements. Profit is increasing as well as weight W is also increasing. No problem. Next, two elements. Here, profit is increasing. Profit increased from 3 to 5. But weight is decreasing from 5 to 4. Is it possible? Well, if we put more number of items, then we'll get more weight, more profit. So more weight means more profit. But here we see that when we have computed, the profit is increasing, weight is decreasing. This is not possible. So the element, the previous element will be purged or will not be included, excluded from the set. Then we will see next two elements, that is 4, 5 and 6, 6. Okay, before that let us talk about the previous. When this is excluded, we had from 1 to 2, 2 to 3 was okay, fine, this is excluded. So let us compare this 2, 3 and 5, 4. 2 is the profit, 5 is the profit, increasing. 3 is the weight, 4 is the weight, increasing. No problem. Profit is also increasing, weight is also increasing. Now let us move further with the next two elements, that is 5, 4 and 6, 6. Now 5 is the profit, 6 is the profit, so profit is increasing. Weight is 4, weight is 6, it is increasing. So no problem. These are valid elements now. So we applied Purging rule to exclude elements. We applied the constraint that the weight should not exceed capacity of max, right, to purge. Now whatever is left out is the actual elements in set 3. What is the, now let us try to find what is the maximum profit and how much weight it gives us, and we have to, what item is put in the knapsack. Maximum, what is the element, maximum element here, which gives maximum profit and maximum? It is 6, 6. Obviously, last element will be that, which gives the maximum profit. Otherwise, it will be purged. So 6 is the maximum profit with weight fit. But we got the 6 as the maximum profit by putting which item in the knapsack. So we will calculate x3 first. Now we go in the reverse order. x3 first. Now what is the weight? Weight is 6. And profit is also 6. So we have 6, 6. Now I told you we will talk about this later. Explain this later. This is set S1 of I is nothing but P, W, profit, weight, and which belongs to SI. Now here, when we are using 6, 6, how did we get this 6, 6? Is it present in S2 or S2, 1? It is not present in set S2. Okay, but it is present in set S2, 1. How did we get set S2, 1? We got set S2, 1 by adding 5, 4 to these elements of set S2. That is how we got this, by adding these. So we added 5, 4. That means we included 5, 4 in the set. So x3 we say 1, including third item. We are including in the knapsack. When third item is included, what will be left? P is 6 minus P3, which will be 6 minus, we added 5, and 6 minus weight is 4, we added 4. So profit 5 is added, profit 4 is added, weight 4 is added. So let us subtract from 6, 6. We get 1, 5 minus 6 is 1, 2. Okay, so that is where this part comes into picture, which belongs to SI. We are looking at how it belongs. Now we need to find where this 1, 2 has come. 1, 2 is here. Now in S2, this 1 comma 2 came from where? Where? Did it come from S1 or S11? Which set did it came? It came from S1. S1 means, S11 means 2 comma 3, that item 2 comma 3 has been added. S11 means that. But S1 means it is not added. So 1 comma 2 is coming from S1 means nothing is added. So X2 will be 0. X2 will be 0. If we add, we will be having that element in Si comma 1. Si1 or S11 or S21. Now let us look at how we got 1 comma 2 in S1. We got 1 comma 2 in S1 by from S0 1. So 0 1 means we added something to S0. That is 1 comma 2 we added. So this will be 1. We added it. We got this. Now if you look at this, P minus P3, P1, sorry, W minus W1, it will be nothing but 1 comma 2. 1 minus 1 will be 0 and 2 minus 2 will be 0. So we get the result as X1 is 1, X2 is 0 and X3 is 1. That is, we add item 1, we don't include item 2, we include or we add item 3 in the knapsack. And the maximum profit which gets yield is, we are computing from 6 comma 6, it will be 6. So this is how 0-1 knapsack can be solved using dynamic programming approach. So this is the algorithm for dynamic programming approach. What we have is, we have S0 as the initial set with 0 to 0. We perform this for n minus 1 time. As S1, n minus 1, we compute this. We then merge, we look at purging rule, we apply purging rule. And after that, in the last step, we try to go and check, create from the previous step, we try to add these values and create px comma wx, that is nothing but p comma w values. And if p of x is greater than p of y, then we make it as 0 because it's not present. Else it is present 1, and then we go back and trace back, in the sense, compute the last element, last item which is placed on not, then second last, third last, the first item. So this is how knapsack problem can be solved using dynamic programming approach.